This problem number 4 is about finding the power dissipated in a conducting medium. The problem is given here. 100 volts per meter. You know what this 100 volts per meter is? That is definitely your electric field intensity because of the dimension volts per meter. Frequency 300 megahertz is traveling through a lossy medium. The medium is lossy. The previous problem discussed in the previous video was lossless. He is having the values of mu r, which is 1. Mu r should be 1 because the medium is lossy generally. Conductors, when we take to find the power dissipation, mu r remains 1. For all electrical conducting materials, mu r remains 1. Epsilon r is 9. Sigma is given the conductivity, so the medium is a conductor. Not so much good conductor because 10 Siemens per meter anyhow. The conductivity, good conductor or not a good conductor or dielectric, whatever is decided by frequency also. We cannot declare as it is. Anyhow, you have to find the power dissipated. Power dissipated generally in conducting medium. As the conductivity increases, power dissipation also increases. So power dissipation is our I square R losses due to, and this is due to conduction current. So the conduction current gives this current. JC is the conduction current density. I is the conduction current. So these losses are predominant in good conducting medium. So that is what is the lossy medium. And find the power dissipated over a distance of 1 micrometer with a surface area of 2 meters square. So the surface area and the length, let me take this. So it's not mentioned circular, rectangle, whatever it is. This area is 2 meters square and this is 1 micrometer. This is what is the dimension of the lossy medium under consideration. So we have to find the power dissipated. And power dissipated is discussed in the Poynting theorem. So recall the Poynting theorem. The mathematical representation of the Poynting theorem is like this. Closed surface integration of the Poynting vector E cross H. Closed surface integration is volume integration of power dissipation density. So E dot J is the density of power dissipated. Volume integration gives total power dissipated in a volume. And the last term is the change of energy stored in a volume with respect to time. That is epsilon E square by 2 mu H square by 2 with respect to volume it is. So with respect to volume dV, the variable. So this is what is the mathematical statement of Poynting theorem. First one is representing power flow into a volume or out of volume. Minus indicates into volume. And this is the power dissipation. Power dissipation or power loss. And this is change in the value of energy stored with respect to time. So what is required for this particular problem is power dissipation. So we shall take out that term power dissipated is equal to volume integration of E dot J into dV. Here J is the conduction current density. So if you want, we can put the subscript C for conduction current density. So we need E and J for this particular problem. E is given in the numerical itself. J is not given, but J can be found from the Ohm's law in point form, that is sigma E. J is equal to sigma E is the point form of Ohm's law. So now everything is converted to electric field E. Sigma is the constant for this volume integration. E dot E is E modulus square. So we need only the electric field intensity to be multiplied by volume. So if you go back to problem, let us see what is 100 volts per meter. The value of electric field mentioned in the problem is 100 volts. I'm sorry, I didn't see the conductivity, which is also required here. Copy all the terms here. Conductivity is 10, is 100. The volume also we need for this. So now conductivity is 10, volume integration of 100 volts square into dV. 10, 100 square is a constant value. Take it out, integrate dV, that gives complete volume of the system. Since electric field is a constant term, integration of dV gives total volume. So the power dissipated is now 10, 100 square. So what is the volume? Recall, the length is 1 micrometer and area 2 meters square. So area into length will give the volume, that is 2 into 1 micro. So this complete calculation 10 power minus 6, here 10 power 4, 10 power 5, 10 power minus 1 is left out, into 2.2 watts. This is the power dissipated in the given volume due to the electric field applied across. Right. So the power dissipated is only depending upon the amount of volume and the value of electric field. Don't forget the significance of sigma. Sigma also contribute for this one. Right. As the sigma increases, conductivity increases, power dissipation. Most important point to be noted is as the conductivity of the medium increases, the power dissipated also increases. That's about it. Thank you.